So we are in video lecture 23 and we see how this happens. So you can now find out what will happen if n is less than 0 and n is less than 0, which should be a mirror image of this. But you can try and find out. Use the same logic. Do it very logically. Don't have to mug up anything. Don't have to. You just follow simple logic and you will be there. In case you have problems, you know you can write it in the Google Classroom. So that should be not a problem. Now we go into case 2 here. Say, for example, we go into case 2 and we draw the diagram once again, TXCO2 diagram, very famous all over the world. XCO2 1.0, this is 0.0, this is temperature, P is equal to constant. Now you see here, we do the same logic and you will see we will come to some interesting results. Now you see here, we take case 2. What is case 2? M is greater than 0. N is equal to 0. So we can ignore this term. N equal to 0, we can ignore this term. So it is always M by XH2 which is important. Because N is 0, regardless of the value of XCO2, M is equal to 0. Hey, this first term is equal to 0 and we have M by XH2 only. Right? M by XH2 and the sign here is negative. So overall the slope will be negative. Simple. Overall the slope will be negative. So let's again do it the same way. Let's say XCO2 equal to 0, which means XH2O is equal to 1.0. Right? Now you see, if XCO2 is 0.0, we are at this end. MXH2O is equal to 1.0. Remember, this term is no more valid. So you will see if M is equal to 1 and XH2O is also equal to 1, then you will have a negative slope, but the value will be finite. So you will have a negative slope and finite intersection. That means at XCO2 is equal to 0 or XH2 equal to 1, so the slope will be negative. Whatever the value intersects, that will depend on LT by del SR. But you have a slope which is negative. Slope which is negative. But if we go to the point where you have XH2O equal to 1.0, then XH2O is equal to 0.0. If this is so, then this value is infinite. Negative. Negative, infinite. So we have negative slope again, but infinite. So if we draw it at this end, it will be something like this. So if you now want to reconstruct the graph, it should be something here. It should be a negative infinite slope, and this will also be negative, but it will intersect it at a finite point. So here, for example, we can take this point here. So we can write here A is equal to B plus H2. This is for case 2. Have you understood? So here you will have A is equal to B plus H2O, N is equal to 0, no CO2 here. And so you will have a slope that terminates here. It will be a finite slope, but negative. And here it would be an infinite slope at XH2O equal to 1.0. Because this is where you have XH2O, where XCO2 is equal to 0 here, XH2 is equal to 0. Here XH2 is equal to 0, because XCO2 is equal to 1.5, you will have an infinite slope. Now, if we go into, we will use a different pen. So if you take now case 3, if I take now case 3, what is here? Case 3. We look at this value. Again we go into, now when you have case 3, your m is equal to 0. So now this term vanishes. This term vanishes irrespective of x h2 values. You know we can't go at x h2 is equal to 0 because if n is equal to 0, 0 by 0 is an undefined value. So we have to have some value, 0.01. It doesn't matter. That is why you see I don't take it very closely. But right now, if we take case 3, then m is equal to 0. That means this term is 0. If this term is 0, then we have a positive slope. It has to have a positive slope. So, and for xco2 is equal to 0.9, then it would be a positive slope. Let's see again. At xco2 is equal to 0, this will be infinite. At xco2 is equal to 0, this will be infinite. So it will be a positive infinite slope for xco2 is equal to 0.0. Right? But if you take xco2 is equal to 1.0 at the other end, xco2 is equal to 1.0, then you will have, of course, a positive slope. Of course, a positive slope because the whole thing is positive. But now you see, if your n is equal to if the n is greater than 0, then this will be a finite intersection. Finite intersection. So you will have a finite intersection. If you do that, then for xco2 0, it will have a positive slope, and at xco2 is equal to 1.0, it will have a finite slope, but positive. So if you join this, then you will have a situation where it's like this. And you will have, A is equal to B plus CO2. So this will be A is equal to B plus CO2. This type of reaction on the slope would be like this. On xco2 0.0, it will have an infinite positive slope, and xco2 is equal to 1.0, it will have a finite but still positive slope. So case 2 and case 3 are just mirror images of each other. You must be very sure when you are studying reading materials which direction is xco2. Normally some people write xco2 here, some people write xco2 here as 1.0, some people write it in terms of xH2O. It does not matter. You just be careful about it. I could have changed the whole term saying the diagram 1.0 xH2O to 0 xH2. It wouldn't have changed anything. So this is an important point where you have case 2 and case 3, where you have A is equal to B plus MH2O, it will have this type of a slope, and if you have A is equal to B plus CO2, it will have this type of a slope. So that is important. And this does not change if you change these values. They only simply, they will change their shape, that's all. The topology will change, but the shapes would not change at all. Let's go into the last of it. We take the last now. So we take now the case number 4. So we will take case 4. And again, we draw the diagram. Temperature, pressure, you remember pressure is constant. xco2 is equal to 1.0, xco2 is 0.0, and this is temperature increasing. Temperature increasing means increasing metamorphic rates. So, now let's see here what happens. Now you see, here, m 4 and 5, m is less than 0, n is greater than 0. M is less than 0, so m is less than 0 and n is greater than 0. So if m is less than 0, this term will become positive. The whole term within bracket will be positive. Why? Because if m is less than 0, then m is negative. If m is negative, the negative and negative cancel and the whole thing will be positive. So whatever you are doing, your slope will be positive. Your slope will always be positive. Now, let's see what happens. At XCO2 equal to 0.0, slope, of course, is positive. And now let's see what happens. XCO2 is 0, the slope is positive, right? So we don't deal with the signs anymore. If XCO2 is positive and XCO2 is 0.0, then this term is infinity. Now it does not matter what is the m value. So this is a positive. It is a positive slope at XCO2 is equal to 0 and infinite. At infinite. The slope is positive and infinite, which means that your curve is like this. Positive but infinite, very steep. Now if you go to the other end, where you have XCO2 equal to 1.0, then again as before, slope is positive. For case 3, for case 4, slope is positive. And you see here, at XCO2 is equal to 1.0, XCO2 is equal to 1.0, here is positive, XCO2 is 1.0, so this is a small finite value, small finite value, but XCO2, but XH2O will be equal to 0 here at XCO2 1.0, XH2O will be 0. If XH2O is 0, then this term will be infinite. So this term is finite, but this term is infinite because XH2O is equal to 0, where XCO2 is equal to 1.0. So here also at this end, the slope will be positive and finite. So now how will the reaction look like? The reaction will look like this. This is how the reaction would look like if you are in this type of a reaction, where you have A plus MH2O, A plus MH2O is equal to B plus CO2. A is equal to MH2O and B is equal to B plus CO2. This is how the reaction would look like. It has always a positive slope and infinite at both ends at XCO2 is equal to 0.0 and XCO2 is equal to 1.0. It's infinite at both ends. So obviously it will be a curve like this to justify it. Now if we go to the other end of the spectrum, we take case 5. What happens? M is greater than 0, so this is negative, and n is less than 0. N is less than 0 means this is negative. So the whole term, slope, will be negative. Here also, the slope will be negative. Why? Because m is greater than 0. If this means that this is negative, and n is less than 0, that means this is also negative. So the total slope is negative. Total slope is negative. So I have written negative and negative for both. Now let's see. At XCO2 is equal to 0.0. Now you see, the slope is negative. At XCO2 0.0, you see this term is infinite. XCO2 is infinite. M by XH2 at XCO2 0.0, XH2O is equal to 1.0. But that is not important because this is a small number. But n by XCO2, XCO2 tending to 0, this will be a very large infinite value. So what you will have is an infinite slope. Which would mean that your slope at XCO2n should be infinite. Right? It will be infinite. And if we go to xco to 1.0, xco to 1.0, then here, this will be a small finite value. xco to 1.0, this will be finite. But xh2 is 0. So this term would be infinite. So again, you would have an infinite negative slope. So that means at the xco to 1.0 end, you will have a slope like this. So now, if you draw it, it's going to be a reaction of this type. So where you will have A plus NCO2 NCO2 is equal to B plus MH2. That's all what it will be. So this is also, you can see, a mirror image thing. It is a mirror image thing. So this is important to understand. This is how the topology of the reactions are in the THCO2 space. You can do the same things for THCO2 space. There is no change in the logic. There is no change in the logic. You can also do it at PCO2. Why I have done at TXCO2 and all books to show it on TXCO2 is because of the thing that which started is progressive metamorphism. That means your time to take the temperature change is an important aspect of the study. An important aspect of the study is the temperature change. So what I have shown you here, that from the thermodynamics of this, from where we get this, these derivations are all I give you, and I have done it again. I have not derived the whole equation. And this is how the slopes of the reaction are in THCO2 space at constant pressure. This is how it looks like. Right? Now we move on to the aspect of progressive metamorphism of the rocks. Now this looks like this. It's a little, remember I told you from the beginning that we make things, keep things simple. That's the first thing we do, is keep it simple. The idea of this course is to tell you about the basics understanding of metamorphic metrology rather than cramming your head with informations which you will not be able to analyze, synthesize and redo it. We need to know, understand things before we do it. And now, based on these reactions, I will try to draw it. So this is the topology of the stable reactions. In this pressure here the pressure I wish to tell you is 2 kilobars. This is the topology or the arrangement of reactions that are stable for the composition CO, MgO, SiO2, H2O, CO2 system. Assuming this H2O, CO2 as fluid present, that means XH2O plus XCO2 equal to 1. This is how the topology of the reactions are. Now, before I go into more details, I will write the reactions for you, balanced chemical reactions for you. So just have some patience. So reaction 1, these are the reaction numbers, 1, 2, 3, what did I get? 4, 5, 6, 7, and 8. These are the reactions. They might be different from the books that you have. So please do the adjustments. This is 5 dolomite plus 8 quartz plus H2O is equal to tremolite plus 3 calcite plus 7 CO2. Next reaction. Reaction 2, which is this. Dolomite plus quartz is equal to dioxide plus carbon dioxide. Reaction 3, and this is the reaction. So for this reaction, it is tremolite plus 3 calcite plus 2 quartz is equal to 5 dioxide plus H2O plus 3 CO2. 3. Then we have 4 now, which is this reaction, and it is 3 dolomite plus dioxide is equal to 2 forsterite plus 4 calcite plus 2 CO2. Now we come to reaction 5, which is this reaction. 5. Tremolite plus 3 calcite is equal to 4 dioxide plus dolomite plus H2O plus CO2. That's 5. Then you have 6 tremolite plus 11 dolomite is equal to 8 forsterite plus 13 calcite plus H2O plus 9 CO2. Then we come to 7, and this is 3 tremolite plus 5 calcite is equal to 11 dioxide plus 2 forsterite plus 3 H2O plus 5 CO2. And the last reaction, which you know very well, is calcite plus quartz is equal to wollastonite plus carbon dioxide. These are the reactions. These are the reactions. Now I will request you to do the following. You try, I have balanced it on some 1 or 3 reactions, 4 reactions. You will find in the PDF that I sent you on this topic. But other reactions are not there. I have derived it for you, and I will request all of you to cross-check whether my balancing is right or not. It is very important. And even better you could do if you do the balancing all yourself, without looking at what coefficients I have. But your reactions all should be balanced. That means all these stoichiometric coefficients are correct. Because, say for example, H2O in this reaction, you see, H2O CO2, 1:9. So this reaction is producing a highly carbonic fluid. But if you look at this reaction, 3H2O plus 5CO2, that means XH2O here, if I just do the calculation, here 3H2O and 5CO2. So XH2O will be equal to, the XH2O of the fluid will be equal to 3 divided by 8, 3 plus 5. So this will be roughly about 0.25 or something like that. No. .37, something like that. So the reaction that is producing 3H2O plus 5CO2. That means in the fluid that they are producing, XH2O is equal to 3 divided by 3 plus 5 is 8. So the producing is XH2 0.37. You know how crucial this becomes. So it is very important that you redo all the equations. I will be happy, I will be a little sad, but I will appreciate if you can do it and say, okay sir, this one of yours was not right. I would appreciate it. But I think it's important that you do it yourself. Right? Now there is certain few things before we go into the more difficult parts of it. You must look here. I am drawing this red line. I'm drawing this red line here. Red shaded portion. This part, you have only dolomite and quartz. You have only dolomite and quartz there. But you see, at this pressure, the temperature at which dolomite plus quartz is stable is increasing with increasing XCO2. Say for example in this reaction H2O is on this side, 7CO2 is on this side. So M is negative here, less than 0. So H2O is gone here and CO2 is more than 0. So CO2 has stayed here. So you know it's A plus B, A plus MH2O is equal to B plus NXCO2. You know how the shapes are. So you can see if you can trace this figure, it's going like this, which is how it should be. Only thing, it has been truncated here. Now you can ask me, sir, how is it truncated there? This can be done based on experiments, or you can do some predictions based on Schreinermacher's grids, with Schreinermacher's analysis of reaction bundles, which you can do it. But it is important that this reaction, tremolite, calcite, dolomite, quartz, is truncated at this point. Is truncated at this point, and then some other reaction comes into play, which is dolomite plus quartz dioxide. In this part, except the very hydrous part, You know here, sorry, except the very carbonic part. Here, XCO2 is very rich. So this part is very carbon dioxide rich. This part is very H2O rich because XCO2 is 0.0. So you can see the stability or the thermal stability of dolomite is increasing with increasing temperature. The dolomite is increasing, the stability of dolomite plus quartz is increasing with increasing temperature because of the slope of the reaction and its truncation so that it gets truncated. You see this gets truncated here. Dioxide plus quartz is dolomite plus quartz equal to dioxide plus carbon dioxide. You know this is A is equal to B plus CO2. You know they should have a finite truncation and a negative slope. So that is exactly what happens. That part is stable here. So when you go to higher temperatures, dolomite plus quartz at CO2 rich conditions break down by the reaction diopside. Dolomite plus quartz becomes unstable because of this reaction. But at less CO2 rich environments, dolomite plus quartz reacts through this reaction. So this is very important. Not always the single reaction leads to extinction of dolomite plus quartz. Till here, dolomite plus quartz produces tremolite plus calcite. But after this value at this end, dolomite plus quartz breaks down to diopside, not tremolite. Not tremolite. So dolomite quartz diopside is a high CO2 environment. Dolomite diopside quartz is a high CO2 environment. Dolomite quartz tremolite calcite is a little more hydrous. Two very hydrous conditions. There is a field of talc which I have omitted, but I think it is better without the omission. You will be able to see it better. Now, having said this, I would like to fix your attention before we go into the greater details. Fix your attention, look at the tremolites where they are. The tremolites. You see, we don't have tremolites on this part. On high CO2 end, tremolite is not stable. Tremolite is stable when the CO2 becomes less. That means in more hydrous environments. And you can see this field. This is the field where tremolite is present. This is the field where tremolite is present. Do you see that? So you have dolomite plus quartz, and then you have tremolite bearing assemblages. We will come into the details of that. But the important point is, at low temperature green schist phases, remember 500 degrees centigrade, this is the green schist phases. 500 degrees centigrade, this is the green schist phases. Green schist phases, amphibolite phases. So here you can see above these two blue arrows, tremolite more or less appears in the amphibolite phases, not in the green schist phases. But you can see tremolite occurring here. So it's not a characteristic mineral that indicates a change from dolomite to tremolite bearing assemblage. No, it doesn't. So you can see the green schist phases to amphibolite phases transition is marked by the appearance of tremolite bearing assemblages. But at the high CO2 end, you don't get tremolite. Instead, you get dolomite diopside bearing assemblages. So dolomite, if you take the same temperature range, at this temperature range, at high CO2 conditions, dolomite plus diopside bearing assemblages become important. But on this side, you have tremolite bearing assemblages important. And this variation has got nothing to do with the change in temperature. This is because of the CO2 conditions of the rock. So CO2 conditions of the rock. So we have then, if you're looking at progressive metamorphism of dolomite across the green schist phases, you have dolomite plus quartz at Greenfish basis conditions, tremolite bearing assemblages in the transition from Greenfish to amphibolites, but at high CO2 end, tremolite is absent. And you have dolomite plus diopside bearing assemblages. And if you look here, here you start getting forsterite bearing assemblages. You can see forsterite bearing assemblage starts to come in at this point. This green line. This is where forsterite bearing assemblages start to come in. So tremolite, dolomite, diopside bearing assemblages are here. So this is, so the stability field of tremolite is like that. Do you see? So another important point I will say before I stop, it is late, I have to go. See, if you go from low temperature to high temperature, the disappearance of tremolite and the appearance of forsterite, they are not same. There is an overlap. And you will see how complicated that can be in the next few classes. But here you see, this is the band over which tremolite is stable. So, in the siliceous dolomites or dolomitic quartzites, the Greenfish to amphibolite facies boundary is marked by the presence of tremolite. But it does not mean that dolomite is gone. No, it doesn't. It doesn't. We will see how complicated that can be. And at higher temperatures in the amphibolite facies, forsterite comes into play. Forsterite comes into play. But it is not that the temperature at which tremolite is exhausted, forsterite is the appearing phase. No, it is not like that at all. So this is the band over which tremolite happens, and forsterite bearing assemblages start to appear here. But here you see, you can have tremolite, forsterite all together. So sorry, I made a mistake here. I should have drawn the line. As the first tremolite bearing assemblages occur here. This is how the tremolite bearing assemblage. Sorry, I just made a mistake. No, let's just go do that. Yeah. So the tremolite field you can see here. This is the tremolite field. I was showing wrong. This is the total tremolite field, but forsterite appearance is at low temperature. Forsterite appearance is low temperature, and diopside appears at even low temperature in equilibrium with tremolite. Have you understood? So that is very important. But above this, tremolite is not present. Tremolite is not present above this green line. It's all forsterite bearing assemblages. So this is overall an indicator of the, this is an overall idea of the phase diagram, but we have to go into greater details. But I think I don't have the time and I have to go somewhere. So I think this is important. This one here, this reaction here, before we go, this reaction here, this is where wollastonite comes in. Wollastonite comes in from a reaction between calcite and quartz. From a reaction between calcite and quartz. But if, for example, at the low temperature there is no quartz, calcite will be persist. Wollastonite will not form. Those particular complications we will do in the next few classes. But for the moment, I think I will stop here and we will continue with this next class. And I will tell you once again, please derive these reactions yourself. Do it yourself. The more you write, you can plot it on the triangular diagram and you can see the intercepts, perfect intercepts, and there you can find out how these reactions have been written. This is two important points here. This is one, this is marked. You see in this, all the reactions that you see going in and coming out, all these reactions that you see, they do not involve forsterite. They do not involve first right. This point is called there is no first right. And if you look at this line, this point, there is no quartz. There is no quartz in any of these reactions leading to the point. And here in this, there is no fosterite. So this is called the fosterite invariant point, I fosterite. And this is called I quartz invariant point. We will talk about them. But for the moment, it is very important for you to know that in this line, none of the reactions contain fosterite. So the invariant point is named by the phase which is absent. And here the invariant point, no quartz is there. So that is why it's called the quartz invariant point. So invariant points is known by the phase it does not have in a multi-component system. So that's it. You can also have invariant points where several phases are missing. But the important point to write is there is no quartz-bearing reaction here. So this is a quartz invariant point. And there is no fosterite-bearing reactions here. So there is a fosterite-bearing point. We will discuss more on this in the next class. But for the moment, this is what you have to study. And please, once again, write down the reactions. Okay, 9th February, that is today, 6th, I will send you a mail. We have an exam. So I think your preparation is good enough. And like last time, you have seen that examinations are not very easy. Open book examinations are not very easy at all. So I think you should be very well prepared with everything because you have access to anything you want. And I can't set you a question where you can do it easily or ask somebody. So it is easy for me to set up a question, not open book question. It's easy to set up. It's more difficult for me to set up an open book question where you will have no support system. Yes, there is a support system, but expected there is no support system because I don't want that you should put on your camera and I should see that you're giving the exam properly. I am not a policeman. I will not do it. You have to find a way by studying, by doing things. Use whatever it is. Talk to whomever you want. But find the solution to the question. Thank you.